And probably some announcements that are worth making. Ooh. But first, let me ask, can people hear me okay? Is my microphone set?
Yes, we can hear you.
I can turn up the gain or whatever, but I see 7 thumbs up. So 8. Thanks, Dunya. Thanks, everybody. Second, how are people doing? People hanging in there?
I'm doing good. Thanks for asking.
We have 3 weeks of classes left, I believe. And then we've got finals after that. We will not, just to remind you, we will not be having a final exam in this class. I don't know if I'm going to try to do a culminating learning target quiz or not, but I think I'm going to err on the side of keeping things simple, and we're not going to do anything different. It's going to be learning target quizzes from here on out, all right? And you will have finals week to work on them. So you'll effectively have 4 more weeks of class to do learning target quizzes. So keep that in mind as you plan your time. This weekend, I sent out updated grade reports for everybody. I caught up on learning target quizzes, on grading them, and everybody received a complete and, to my understanding, accurate learning target quiz report. So you should see where you are in the course. In the email, I invited everybody to let me know if they saw any mistakes or had any questions, and I got several responses. Several people reached out to me. And so I helped people understand what the report meant to them, or they helped me see where I had made an error. So take that invitation to give me feedback seriously. We're in this together, and I want you to make sure that you know exactly where you stand in the class. Since sending those reports out, other people have taken learning target quizzes, so I will try to get to those and grade those as quickly as I can. If there's a learning target area that you need to demonstrate mastery over, but there's not a quiz for you because you already took the one that's there, for example, email me and I'll write a new one and post it, but I'll also just send you a PDF of the quiz directly, so you don't have to go through the process of downloading one. I know one person did that this weekend. I think that worked out okay, but just let me know. I know there's a couple places where I need to post some. What else do I want to tell you? Okay, so we're up to 18 folks. Hey, so Lupe, why don't you remind people what's happening with you and your drop-in hours and stuff?
Hello, everyone. Good morning. For this week, my drop-in hours are still going on from 7:30 to 8:30 on Wednesday. And then if those hours don't work for you, you could go on the campus page, and there's other hours down there. I will be at the STEM Center. For the following week, those hours are not going to be available because of Thanksgiving break. The STEM Center decided to close the STEM Center at noon, so we didn't make the cut for that day. So next week, I won't have any hours for you guys to come in, and then I'll go back to be normal the following week.
Okay, and then you won't have any hours over finals week because you take finals too. I'm sure you don't have any hours over finals week, right?
I'm not sure on that yet how that works.
Yeah, why don't you check and you can let us know on Wednesday.
I'll let you.
Okay, thanks, Lupe. So Jet, you asked, will you be activating the rest today? Oh, the other quizzes? I'll post other quizzes for which there's gaps today too. Yeah, that's my intention.
Yeah, there's actually I think 3 up there that don't have like they're there showing, but they're not active. So
okay, yeah. Thanks. I'll put some of those up there then. What else? Is there anything else going on in the world that we should know about? We haven't talked for a whole week, right? We didn't meet on Wednesday because of Veterans Day. It's been a long time. Anything else we need to know about? Anything else you want to share with your classmates? Lots of shopping, yeah. Has registration started for the spring semester yet? I imagine it has. For some people. Tomorrow. Good. So you should be thinking about taking Calc 2. I'm teaching Calc 2 in the spring, and I'll be teaching it in the same way. I believe with learning target quizzes and things. I haven't taught it in this fashion before, so I've got a lot of work to do over break if I do that. So consider that. I'd love to have all of you in that class. What else? Oh, hey. So what's the big news on the COVID front since we talked last week? I don't think we talked about it on Monday. The shutdown, Mason says. I haven't heard Friday. Oh, Friday? Do you think there's a shutdown happening on Friday? I have not heard about that. But yeah, Dunya, the vaccine was the big news. Yeah, Mason?
I just heard at work, like, I mean, it was coming from like a 20-year-old too.
Yeah.
But I heard Friday we might go into another, like, where like the extra things are shut down, but everyday life is still the same. Like the restaurant, bars, gyms, like all that.
Only essential workers working, maybe, kind of thing. Yeah. The numbers in Ventura County have been pretty shitty. I'll show you here. Okay, I'm gonna see, how should I do this? I will show you. I'm gonna share a different screen with you. This is my application in which I do statistics. So let me see if I can blow this up a little bit. Yeah, I think this is the one we want. I think this is the one. Yeah. So here, let's see if this works. Down here in the right corner of the screen, you see this? This is, maybe I can blow it up. Let's see if that works. Oh, that's pretty gross. This is a plot of the infections, COVID-19 infections in Ventura County since like February or March, since they started keeping track of the numbers. So you can see here in the summer, we had this big frightening peak and it came back down, and now we're headed way back up there. And you can see there's these really high numbers. They're not higher than they've ever been, but they're still pretty high. So this is where we're going in Ventura County. And yeah, it's pretty dire. When this was happening in July, there was all kinds of fear about, there's all kinds of fear about hospital bed availability and stuff. I don't know how to do this. There we go. So those numbers look pretty crazy. And the California numbers look kind of crazy too. California has different tiers. Maybe let me share a browser with you for a second. Browser. Let me share the browser. Where is it? There we go. California. Here's the California webpage for COVID-19 data. And let's see, recent updates. Where did I want to show you? The state dashboard. Yeah, so here's the state dashboard. Here's the number of COVID cases in California, and there's this big swoop that's happening statewide. We see that in Ventura County too. If you look at a bunch of the counties across the state, a similar sort of thing is happening. the scales are different, right? Different counties have different populations. And so the y-axis is different in the different counties. You can look over here at the deaths and you see the deaths looks like they're going down. So you could say, hey, Miller, don't get too excited. Look, this is a good thing. But if you compare the peak here is like August 18th with the peak here, which is July 22nd. The deaths follow, they're a lagging indicator. They follow 2 or 3 weeks behind the infection rate. So we're going to see, so this started climbing October 18th. So we're not even 2 weeks past, we're close to 4 weeks, 3 or 4 weeks. So expect this deaths to increase, but we've got better treatments now. So that might slow that down a little bit. But this is a good dashboard. Let's look at Ventura County, see what they say about Ventura County. So here you can see it. Ventura County is the blue curve and California is the gray curve. Similar sort of dynamics locally versus statewide. So testing data, you can see here in Ventura County, we've really increased our testing, which is good. I might even go get an antibody test this weekend or later this afternoon. But Ventura, or the state, has these 4 different levels of COVID risk. Right now, Ventura County has been in the red tier, and I think we're right here. No, right here. We've been in the red tier, but like Mason was saying, something's going to happen, and a lot of people think we're going to be moving to this purple tier, and that's where a lot of non-essential things get closed. Our numbers are definitely put us in the purple tier, and we'll hear tomorrow if the local health officials tell us that, or the state, I guess the state will tell us if we're in the purple tier. But there's the vaccine right there. There's the vaccine. So what have we heard about the vaccine?
Well, there's
Go ahead, Jesse.
There's 2 companies. Pfizer, they have their vaccine. It has like a 90% effectiveness rate, and then Moderna, they announced this morning 94% effectiveness.
Yeah,
we have 2 vaccines now.
Yeah. So there's 2 vaccines as of this morning. So that's pretty exciting. And the data that they've been reporting, people like it. Dr. Fauci, the national expert on infectious disease, he says he's cautiously optimistic about the numbers. So this is a good thing. And some of those vaccines they're predicting might be available to frontline health workers by the end of this year. So that's like in the next 8 weeks, right? No, 6 weeks. We only have 6 more weeks of 2020. I'll be excited to be out of 2020. I don't know about you. But next year we'll see how many of those vaccines are able to be distributed nationally and internationally. Of course, Pfizer, it's an international company. They're going to have 1.3 billion doses available by the end of next year. And each treatment consists of 2 doses. So, that's, 650 million treatments. And they'll be shared worldwide. So who knows how many America will get. But what was the name of the Moderna's vaccine that was announced today? They're an American company, and they were recruited by the U.S. government. They committed to the U.S. government to sell their vaccine to the U.S. So they're going to have maybe half a billion vaccines, they think, by the end of next year. There's one big difference between the 2 vaccines. They both seem like they're about equally effective in preventing infection. Anybody know the big difference between the 2 vaccines? One big difference between them? So, and this is relevant to us because we want to get back to normal. The Pfizer vaccine must be kept at a very cold temperature. If it's not kept at a very cold temperature, it breaks down, right? And then just becomes ineffective. The Moderna vaccine can be maintained at a refrigerator temperature for quite a long time. So that has implications for distribution. Right? the Moderna vaccine might be more appropriate, or it might be easier to deliver to rural populations and things that don't have deep freeze capabilities. Whereas the Pfizer vaccine, maybe it's going to be more likely distributed to metropolises and things where they have large medical facilities that can keep things at a very, very cold temperature, like negative 70 degrees Celsius or something. And I'm American, so I don't really know what that temperature is in Fahrenheit, but cold. So if you don't keep your eyes on the news, watch the news, be informed about how this stuff is going to affect us. I have some thoughts on how it's going to affect us at CI. We can talk about that at another time. But I just wanted to make sure that you all knew the news. It's good news. It's not going to fix everything, and a lot of people are vaccine shy. So, yeah, who knows? Who knows what having a vaccine is going to do to the United States? So, Jet, you say everyone you know that had it didn't think it was too bad. That had COVID. Oh, wow. I mean, there's a variety of ways it can affect people, and people don't know the long-term effects so much either. So, lots of people are affected very differently. So, and you just, I don't want to bring it home to my kids or my parents or my grandparents, right? So, we just need to be careful. All right, but this is not this is not what's the class would it be? An epidemiology class. This is a math class, so we should probably start talking about some math. So I am ready to do that. Let me share my tablet. All right. So this is November 16. And we're going to continue our conversation that we started last time. Last time, we talked about finding global extrema of functions. And we used what's called the extreme value theorem. And it says that if your function is continuous on a closed interval, then it has both at least one absolute maximum or global maximum and at least one absolute minimum. So that's what the extreme value theorem says. And last time we talked about how to use it. And the way we use it is we look for critical points of the function, because we know that extrema, maxima and minima, occur at critical points. And critical points consist of endpoints, singular points, places where the derivative doesn't exist or isn't defined, and stationary points, place where the derivative is zero. We find the critical points and then we compare the critical values. And that's how we identify which critical point is our absolute maximum and which critical point is our absolute minimum. You could have more than one absolute maximum. In that case, you'd have two critical points that would have the same critical value, the same biggest critical value. Likewise, you could have more than one absolute minimum. You just have two critical points that had the same absolute or critical value, the smallest critical value. An example of a function like that would have more than one absolute maximum would be the cosine function. And it also has more than one absolute minimum because it's periodic. Okay, so what I want to do today is extend this. The idea of a local maxima or a local minima, not or, and. So the word local is important to us. That means like nearby, right? So a local maxima is one where it's a point where the values are bigger than its neighboring values. Compare that with this idea of absolute maximum or absolute minimum. That absolute is meant to convey the idea that those values, like an absolute maximum, those values are bigger than every other value of the function. Sometimes we use as the adjective for such a point a global maximum or a global minimum. And that's an adjective that contrasts nicely with the adjective that we use for local maxima and local minima. So global means over the entire domain. So a global maxima would be one whose value is bigger than all other values of the function over the domain. Whereas a local maxima is one where the values are close to one where the values are bigger than the other values nearby. So here's a graph of a function. It might be like a degree 4 polynomial or something. The way I drew it, you can see this point corresponds to a global max. This point here is not a global maximum because the values around here are definitely smaller than the values around here, or definitely smaller than that value. But at this point, the value at that point, it's bigger than the values nearby. And so this is an example of how a local max might appear. Right? Because locally, in a neighborhood, the value at that local max is bigger than the neighbors. So we'll talk more about this today. But let's do an example first. It's been a week since we've talked about it. Let's just do an example to warm this stuff up, remind ourselves about this. And it turns out a lot of these ideas that we'll use will also recycle to understand these ideas. Any questions so far? I don't hear anything, but also my chat window has disappeared. So let me see if I can find that. Okay. So let's do an example. I don't see anything in the chat. Let's find an absolute, or let's find all absolute extrema. That is all the absolute maxima and absolute minima of the function f of x equals 4x over 1 plus x squared on the interval from -2 to 3. I'm going to start this problem, and I'll probably work through it nice and slowly. And I want you to make sure you understand all the steps that I do, because soon we're going to do some we're going to do some examples, and I'm going to throw you into breakout rooms to work on some things in pairs or triples. So just be prepared for that, and make sure that you ask questions about what I do in case you're concerned that you won't be able to do them on your own. Okay, find all absolute extrema of this function. So this sounds like a job for the extreme value theorem. So can we use the extreme value theorem? That's a question that we need to answer. the extreme value theorem works for continuous functions on closed intervals. So we need to ask ourselves, is our function that we're studying continuous, and is it defined on a closed interval? The easier of these two questions to answer is the second one. Is the function defined on a closed interval? Well, we're told we want to look at the function on this interval. And that interval is definitely a closed interval. So we can answer yes to the second question. So the harder of the two is the function continuous. We have to look up here. So I'm going to ask you a 3-2-1 question. And so to remind you what that means, I'm going to ask you a question. You're going to think about it for a couple moments and type in the answer that comes to you into the chat, but you're going to not hit enter. I'm going to say 3, 2, 1, go. And when I say go, you hit enter. So everybody's guesses cascades through the chat. So the question I'm going to ask you for this 3, 2, 1, go exercise is this. What kind of function of this is this? Of all the families of elementary functions we reviewed at the beginning of the semester, what type of function is this? What's this called? What family does it belong to? So think about it for a moment. Type your thought into the chat. And I expect everybody to be able to guess something. So I'm going to expect 18, 17 answers over in the chat, 17 guesses. There's no harm for getting a guess wrong. I expect everybody to get it, but if you don't get it, I mean, that's okay. You'll learn. Okay, 3, 2, 1, go. All right, that's not everybody, but that's, about a third of us. The answer is it's a rational function. A couple of people said it's a polynomial, and that's a reasonable guess, except polynomials don't have fractions with variables in the denominator. So a rational function is a ratio of two polynomials. So this is a rational function. Can a rational function be continuous? Can somebody throw in the chat, yes or no? What do you think? Anybody else? Jet threw something over there. Summer says yes. Jet says yes. Robert says no. Selena says yes. The answer is yes. Rational functions can be continuous. In fact, rational functions are almost always continuous. The only problem rational functions have is when you get division by 0. A rational function is not continuous when you get division by 0. So if somebody asks you if a rational function is continuous, you should say, give me a second, let me check. And then look at the denominator and see if the denominator ever vanishes. A rational function will be continuous at almost every point in its, well, it will be continuous at every point in its domain. That's a good thing to remember. Division by 0 is where the function is not defined. So those are outside the domain. So is this function continuous on our interval? That's what we want to know. Well, look at the denominator. It never vanishes. This never equals 0. Because if you set 1 plus x squared equal to 0, you'll get x squared equals -1, which is impossible because x squared is always a positive number. So here you're having 1 plus a positive number that can never be 0. So f of x is continuous. F of x is continuous everywhere. And specifically, it's continuous on this interval. So we can use the extreme value theorem. So to use the extreme value theorem, we need to list all the critical points of the function. So there are 3 types of critical points. There's endpoints, There are singular points, and there are stationary points. So singular points are where the derivative of the function is not defined. That's like with the absolute value where it comes to a point. It's not differentiable at the 0 input. And the stationary point, that's where the derivative equals 0. So let me just write those little notes since this is the first time. So when the derivative equals 0. The easiest of these, of course, are the endpoints. The endpoints we know are x equals -2 and 3. The singular points are rational function. It's differentiable everywhere it's defined. And so it has no singular points. Right? So NA does not apply. No singular points. So the stationary points, this is going to take a little bit more work. So let's do a little scratch work over here. We want to solve f prime equals 0. So what's the derivative of this thing? Well, the quotient rule, derivative of the top times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. So multiplying out, I get 4 plus 4x squared minus 8x squared. Oh, that's convenient. And so I end up with 4 minus 4x squared over 1 plus x squared squared. Common factor upstairs of a 4. Can factor that out. Right, so that's my derivative. So now solve, setting that equal to 0. So I can multiply both sides by the denominator. That is, I can clear the denominator. So those cancel. And then over here on the right-hand side, 0 times anything is 0. So I'm just left with my numerator equals 0. And I could divide both sides by 4. And the same thing happens. That 4 cancels with that 4. And so I'm left with 1 minus x squared equals 0. So that factors into 1 minus x times 1 plus x. And you can see, looking at that the solutions to this equation are x equals 1 and -1. So I'm going to write that over here to the left. So we found all our critical points. -2, -1, 1, and 3. So the next thing we do is we plug these critical points back into my function f to find the critical values. So f of -2, f of -1, f of 1, and f of 3. And if you plug these into the function, you get -8/5 for f of -2. You get 6/5. Oh no. For -1, you get -2. For f of 1, you get 2. And for f of 3, you get 6/5. So looking at these, you see 2 is the largest of these critical values, and -2 is the smallest. Or maybe I should say, let's do this, greatest and least. Those words are better for a number line, okay, for use on a number line. Both 2 and -2 have the same size, so saying biggest and smallest doesn't quite make sense. But there we go. So this tells us that the function f of x has one absolute max on the interval from -2 to 3 at x equals 1. And it has one absolute min at x equals -1. Then we're done with that problem. Okay, anybody have any questions about that process? It's the same process that we used last week. And it's a process for using the extreme value theorem. Okay, looks like we're good. Nobody's saying anything in public or in private. So let's talk about local extrema. You cannot use the same process to find local extrema. This doesn't give you enough information to determine which of these is a local minima or a local maxima. You might be able to do some logical deductions to figure some things out, but those would be very specific to the function that you're looking at. So what I want to present to you is a technique that will work for all functions. It'll build off what we've learned in the extreme value theorem case, in the sense that it's going to use critical points, but it's not going to use critical values. It's going to use something else. Every absolute max is also a local max. So this is a good observation to keep in mind, that every absolute maximum also happens to be a local maximum, but the reverse is not true. But this should make it clear that local extrema must occur at critical points. If you think about it, if you have a local extrema and then you chop down the domain of your function just to include that one point and maybe a few points around it, then that local extrema suddenly becomes an absolute extrema. So it makes logical sense that local extrema have to occur at critical points. And those are endpoints, stationary points, or singular points. But here's how we're going to tell local minima apart from local maxima. Since I told you we can't use critical values to do it, we're going to use something else. And we're going to use what's called the first derivative test for local extrema. Sometimes we just abbreviate that first derivative test, but I'm going to add this phrase for now, so it's clear in our notes that that's how we're using it. So here's the theorem: let f of x be a function defined on an interval that contains a critical point p of f of x. Then I'm going to have to move to the next page. It's going to take too much space. Let me copy this over. So the first case, P is a local maximum if at P, the derivative changes sign from positive for x less than P to negative for x bigger than P. Okay, so I'll draw a picture of what that means. But what this is saying is that a point is a local maximum if, when you look at the derivative function To the left of P, the derivative is positive, and to the right of P, the derivative is negative. The opposite happens at a local minimum. So P is a local minimum if at P, f prime of x changes sign from negative x less than P to positive for x greater than P. That's the theorem. Yeah, that's the theorem. If P is a critical point and the sign of the derivative doesn't change, then it's neither a local max or a local min. So why does this work? Remember that f prime is bigger than 0. It means f is an increasing function. Okay, it's going up. F prime less than 0, the derivative negative, means f is decreasing. So if we have a function that has a critical point P, and to the left the derivative is positive, so we're going up, and to the right the derivative is negative, so it's going down, then that makes sense that P needs to be a local maximum. And the way we record this, the way we investigate this is using a chart of signs. So at P, we see the derivative changes sign from positive to negative, then we can conclude that P is a local maximum. And here's the picture for a local minimum. You can see on a chart of signs, the derivative goes from negative to positive. And when I make a chart of signs, so when we're doing problems, we're not drawing pictures like this. This is what we're going to be seeing in our mind's eye eventually. This is what we're going to try to be arriving at. I'm just trying to show you the nature of what a graph does in relationship to its derivative. We will calculate these charts of signs. And so when I'm calculating with these, what I like to do is I like to draw in little arrows that show me where the function is going up and the function is going down. And once I draw these arrows, it's obvious to me that my function has a local maximum there. Over here, it's obvious that my function has a local minimum there. These arrows help me see that. Okay. So the theorem tells me what's happening, but these arrows are a little bit more visual clue to me as a human being with this overdeveloped visual cortex. And I'll do examples of these to show you how this all works. One final note. The first derivative test for local extrema, it kind of doesn't address endpoints. So what you need to know about endpoints is this. So suppose I've got a function on an interval from A to B, and it looks like this. Well, you can see from the picture that what I have is a local minimum. But when we have a chart of signs and we put, let's draw this the right way. We put that critical point on our chart. We'll calculate that the derivative is positive to the right of A, but the derivative isn't defined over on the left side of A because A was an endpoint. But if I draw that arrow there that goes up to reflect the fact that my function is increasing there, it suggests to me that A is a local minimum. Similarly, if I'm on the other endpoint, my function's doing that. What is my chart of signs going to look like? Well, my derivative is going to be negative there, and I'm not going to have any derivative over there because my function is not defined to the right of my right endpoint, well, my little arrow is going to help me see that indeed this endpoint has to be a local minimum. So you need to be a little bit thoughtful about, how you use the derivative test to determine what kind of absolute minimum you have at an endpoint. And these arrows help. These arrows help you do that. So let's do an example. Let's go back to the previous function and apply the first derivative test to it. It's the same function, same interval. Now I'm just asking to identify the local extrema. You could look at this and you could say, well, I've got a continuous function on a closed set. I can use the extreme value theorem. And that's natural for you. It's a natural thing for you to want to do, but you can't do it because the extreme value theorem does not tell you anything about local extrema. So we have to use the first derivative test. So for the first derivative test, let's look back at it here. What do we need? Well, we need to know the critical points. Right? So we have to know all the critical points P. And then we need to look at the signs of the first derivative. So let's make that list. Need critical points. And so that's the endpoints, stationary points, and singular points. And we need the derivative. So let's recycle the work we already did. We know the endpoints are -2 and 3. We know there's no, we know there's no singular points because the function's a rational function. It's differentiable everywhere it's defined. And the stationary points we calculated are ±1. So we have all the critical points we need to work with. So we're set there. Now, what we didn't have back there, we didn't have to use the derivative. Well, I guess we did. We had the set where the derivative was equal to 0. So maybe we can just copy that. Do we have that? Yeah, here we go. So let's just copy that. There's our derivative. 4 times the quantity 1 minus x squared, all divided by the quantity 1 plus x squared squared. Four times the quantity 1 minus x squared, all over 1 plus x squared squared. Okay, so now we want to know when this function is positive and when it's negative. So we're going to make a chart of signs. And this is an important thing for you to be able to do. I talked about this last week. I've talked about it earlier in the semester. You got to do it. You're going to think you can get by without doing it, but no, you got to be able to do it. So we're going to make an axis, and I'm probably going to have to copy this over to a page with more space. We're going to make a number line that corresponds to the sign of my derivative. And we're going to put on that number line all of my critical points. And don't worry about spacing them out proportionally or anything. Just put them in order. And now what I'm going to do is I'm going to make a column over here of the different factors that can affect the sign of my derivative. So I'm going to factor this whole thing. And I did that in my previous work, so this won't come as a surprise. My denominator can't factor anymore. This is an irreducible polynomial. You try to factor it with a quadratic and you'll get imaginary numbers. So I'm going to put 1 minus x, 1 plus x, and then 1 plus x squared squared here. And then down at the bottom, I'm going to put f prime of x. Because if we take, and what's going to happen is that if we multiply this by this, and then divide that by this, and then multiply everything by 4, we're going to get the derivative. Now, multiplying by 4 will not change the sign, SIGN, of everything here. So what I'm going to be keeping track of is what's the sign of this factor, and what's the sign of this factor, and what's the sign of this factor. And then when you multiply and divide those all together, the signs of the factors determine the whole sign of this. So here's my chart. So I'm going to do the easy factor first. I'm going to do this factor. Actually, I missed a 2. Oh, no, it's right there. That factor is always positive. So on those 3 subintervals, that 1 plus x squared quantity squared is always going to be a positive number. It's not going to affect the sign of my derivative. Okay, so let's look at the first factor right here, 1 minus x. So on this first interval here, from -2 to -1, if I plug in the number here, or if I plug in a number in this interval into this factor, what sign am I going to have, a plus sign or a minus sign? So I want you to think about it for a second. Is it, and we'll do a 3, 2, 1, go, right? Let's do a 3, 2, 1, go. What sign does this factor have on this interval? Don't tell me how you got it, but just tell me what sign it's going to be. I want everybody to answer. Everybody should be able to do this. We've done this before. Plus or minus? 3, 2, 1, go. Yeah, everybody who's responded has got it right. It's going to be a plus. If you're sitting there wondering why do we know it's going to be a plus? Well, it turns out these critical points here are the only place this is going to change sign is when it's 0. And this is 0 when x is 1. Okay. So this is the only place it's going to change sign. So I can pick a number and plug it in here, and that's going to give me the sign on this interval. So I'm going to pick -1.5. You plug that in here, you get a half. So that says my function is going to be positive there. Play the same game on the next interval. I'm going to plug in 1/2. No, I'm going to plug in 0. Plug in 0 to this, you get a positive number. And on the last interval here, I'm going to pick 2. Plug a 2 in here, I get a negative number. So that's what the sign of this factor 1 minus x looks like. Technically, you could ignore what's happening here and just look at it on this interval and on this interval, since you know it only changes sign here. But I don't even do that when I do this chart of signs, so I don't think you should either. So it's 8:56. So let's take a break. And I'm going to take a 6-minute break, because the first minute of the break, I want you to decide, how do you fill in this next row? Okay. Fill in this row. And when we come back from break in 6 minutes, I'll do a 3, 2, 1, go. And I'll ask you to post the order of the pluses and minuses in that row. Okay. So don't do it before then. Do it when we get back. Okay. 5-minute break plus that. I'll see you here when we're done. We're back. Let's do this. Oh, it looks like my iPad tablet went to sleep. Let's make sure it's sharing again. I asked you before you gave yourself a little break to figure out what three symbols go on this row. So the factors, the factor 1 plus x, plus or minus, plus or minus, plus or minus. And I'd be prepared to throw this into the chat for a 3, 2, 1, go, which we're going to do right now. What do you think it is? What's the pattern? 3, 2, 1, go. So I'm looking at what's showing up. Yeah. Okay. Thank you for playing. Let's work it out together. I'm glad everybody has tried. Everybody did something. So 1 plus x, let's make it simple. I'm just going to pick a number from each interval and plug it in there and record the positive or negative sign. So in this interval, I'm going to pick -1.5. So I put in -1.5 for x, I get -0.5. So that tells me to put a minus sign here. On this interval, I'm going to take 0 because it's my favorite number. Plug that into 1 plus x, I get 1, so I get a positive. And then on the last interval, I'm going to pick 2, throw it in here, I get 1. 1 plus 2 is 3, so that's a positive number. So there you go. Negative, positive, positive. That's what the answer should be. And a couple of you got it. What I did, the pick and plug method, that will always work. As long as you've got all the critical points in your chart, the pick and plug will always work. For any one factor, like for a degree 1 polynomial, it can only change sign once. So I know I'm only going to see one change of signs in that row. This process of making a chart of signs takes a complicated function, breaks it down into simpler pieces, and then we reassemble into our complex function. So now let's reassemble. I'm going to use a different color. I'll just use a gray. So what's the sign of f prime on this first interval? Well, we've got a positive times a negative divided by a positive. So the way positive and negatives work with one another, you're going to get a negative. And remember, dividing by a positive number is the same thing as multiplying by its reciprocal, which is also positive. Dividing by a negative number is the same as multiplying by a negative number, its reciprocal. So for all intents and purposes, you can say a positive times a negative times a positive is a negative. Okay? A positive times a positive times a positive is a positive. And a negative times a positive is a negative. So that's what my chart of signs looks like. A negative, positive, negative. And this is the money row. This is what gives us all our information. Because it tells me on this interval, my derivative is negative. On this interval, my derivative is positive. And on this interval, my derivative is negative. So this is where I get to put in my little arrows. So before I proceed, let's copy this mess where we have more space. So this chart tells me that my derivative is increasing on this interval, then it changes directions at -1 to become decreasing, and then it changes directions at 1 to become increasing. So the first derivative test it tells me x equals -1 is a local maxima. And x equals 1 is a local minima. The chart of signs tells me x equals -2 is a local minima. and x equals 3 is a local maxima. And that's how we use the first derivative test in a chart of sines. Good? We're going to take it one step further. And I'm going to point out to you that we can use this information to graph or to sketch the graph of a function. So in this case, let's create the axes here. And I'm going to put my critical points here. And this I'm going to try to do proportional because we want the sketch to look okay. And I think we also computed the critical values of the function. So let's put those in. At -1, I think we had 2, and at 1 we had -2, and at -2 it was a little bit lower than 2, and at 3 it was a little bit bigger than -2. I'm going to do these in a different color. Those are critical values. And then, all right, so those were our values. And it's from those values, we can conclude, or we can identify the global maxima and the global minima, right? Here's the global max and here's the global min. But now if you look at this chart here, it allows us to start the process of sketching. I know on the interval from -2 to -1, my function's increasing. My function's also increasing from 1 to 3. And then from -1 to 1, the function's decreasing. So this is a really rough sketch of what the graph of my function looks like. And if I were to fill in those dotted lines, I get that. Can somebody tell me why that's a bad representation of the function? What I just did? Either vocalize it or throw it in the chat. There's something about this that's bad. Can somebody, with a capital B, can somebody tell me what it is? As I pour some coffee. Anybody want to guess?
Isn't the derivative not defined when two lines intersect at a point?
Oh, so you're like,
there's like a corner kind of
right here,
thing.
for example? Yeah, exactly. What I sketched here is a function that's not differentiable here or here. But my function f is differentiable, right? Everybody see that? So this is an unfaithful representation of my function because I've created a feature that I know does not exist in my function. So I need to do a little bit better. So let's see if I can do that. Okay, so I took away the solid line. What I'm going to do instead is I want to draw this so I know that my function's differentiable. So I'm going to smooth it out at each of those points, and then I'll connect. Connect in a way that respects the monotonicity. It reflects or respects the direction of my function. And so there, my green graph is a little bit better. It's better in the sense that it's nice and differentiable at each of those points. So this is what I call a decent sketch. And when we sketch graphs using the first derivative test, this is about all I want you to do. This is what's important to me. Is -1 supposed to be a minimum? Not according to the analysis that we just did. But wait a second. according to our original analysis, it was, right? So did I get these values wrong? F of -1 is -2. This is not making me happy. Thinking. Give me a second while I think. Yep. Yep. So what the hell did I do wrong? So let's see. Let's find the error. So we're starting here. I've got my function, calculating my derivative. Yeah, there's definitely something wrong here. So the derivative of f, derivative of the top is 4 times the bottom minus the top times the derivative of the bottom all over the bottom squared. 4 plus 4x squared minus 8x squared. So this all checks out. Okay, so that's good. That's looks okay. That looks okay. Oh, yeah, Luke. Luke was very polite and privately messaged me. You know, not gonna put Luke in the position where he has to do this. I'm gonna do it for him. So this is, I threw into chat what Luke just said to me. Isn't it supposed to be decreasing from -2 to -1 instead of increasing? And Luke was looking at this. Decreasing, increasing, decreasing. Absolutely. And what did my stupid butt do? It put these arrows in the wrong direction. Good catch, Luke. So it's supposed to look like this. So let's go back here. So looking back at this and fixing it accordingly, according to my arrow diagrams, -1. Okay, and I lost that minus sign there. -1 is going to be a local min. 1 is a local max. And then -2 is a local max. And 3 is a local min. So my decent sketch should look like this. So at -1, I should have this, and then at -2, it looks like that. At 1, I'm up like this. So my first rough approximation looks like that. And then when I fix it to smooth things out, my graph is going to look like this. Right, I can fix that. I can do that better. All right, now there's my decent sketch. Okay, good, we fixed it. Thank you. I'm sorry that I wasted all our time with that. So there's a couple other things that, if without using any calculus, we could do better. Can anybody look at this graph and say that show me something that we could do better in the sketch? Now, as a hint, I only used the critical points and critical values, and then the monotonicity information. Is there anything else about this graph that a pre-calculus student could do better?
Make it continuous on like the x-axis, so it goes on forever.
Yeah, except that we're told that the function is only defined on the interval from -2 to 3. So I don't want to add anything new into the problem at all, though that would be interesting to ask what happens if we grow the domain, but that's not what I'm asking about right now. There's something that this graph has that I didn't do a decent job approximating, that if I added it in, it'd be easy for me to add in and I'd get a better sketch. This is a decent sketch, but I can get a decenter sketch. Anybody else want to take a crack at it?
Can I give it a try?
Yeah, Lupe, yeah, sure.
Are you talking about the x-intercepts?
Yeah, and the y-intercepts. Right, so the y-intercept, that's the point 0, comma f of 0. And the x-intercepts, they're the points f of x naught, comma 0. So it's easy for us to calculate. I mean, this one's super easy, right? Just plug 0 into our function. And if we do that, we get 0, comma 0. So our function should have gone through 0, comma 0. And it turns out if we do the analysis to see what the x-intercepts are, it only has 1. It only has the 0, 0. So I could make a better sketch if I included the fact that I knew its x-intercepts and y-intercepts. That's all I'm trying to tell you. Okay, that would be a freebie from a calculus perspective. Okay, let's do another one. Do you want to do this in breakouts, or do you want to do it as a class? Anybody have any opinion? Doing your says as a class? Jet, class. Okay. But I want everybody to have some scratch paper out and do this along with me. Okay. So I'm going to give you a function, and then we're going to go through the whole process of trying to sketch a graph of the function. But we're going to break that down into the process of answering the following questions. So I want to find the critical points of the function g of x equals 5 plus 12x minus x cubed on its domain. And then, so we'll tackle that question first, and then I want to find the intervals on which g of x is increasing. And then I want to find the intervals. We'll look for them at the same time, on which g of x is decreasing. And then that'll give us the tools to use the first derivative test to identify local extrema. And then we'll end by sketching. So one thing, find critical points. Second, find out where the function's increasing and decreasing. Third thing, use the first derivative test to identify the local extrema. And fourth thing, sketch the graph. Okay. So number one, find the critical points on the domain. So can somebody throw in a chat or vocalize what's the domain of this function? Should be fast. You should get it fast. What are the set of x's you can plug into this function? That's right, Brandon. All real numbers. Polynomials are defined everywhere. So the domain is all real numbers. I'll use the symbol for the real line. So we want to find the critical points of this function on its whole domain. So critical points come in three flavors. So write this down on your scratch paper. Quiz yourself. What are the three flavors of critical points? I'll give you 15 seconds. Okay. You should have endpoints, singular points, and stationary points. That's what you should have written down. Now, with that in mind, let's figure out what kind of critical points our function g has. It has no endpoints. No endpoints because the domain is all of the real numbers and we're asking what are the critical points on the set of all real numbers. So not applicable. No endpoints for the real line. How about singular points? How do we find its singular points? Does it what are its singular points? Anybody? What are the singular points of our function? Oh, somebody guess. You know it. It's not a trick question. Where is this function not differentiable? Yeah, Luke. This is differentiable everywhere. It's the most beautiful function that has no points ever, right? It's a polynomial. Polynomials don't have any vertical asymptotes. They don't have any pointies. So they're always differentiable. So when we're looking for critical points, there are no singular points for polynomials. So finally, stationary points. Hopefully there's some stationary points. Otherwise, our function has no critical points, which is possible. A linear function doesn't have any critical points, but this isn't linear. Let me ask a question. Do we so here's a 3, 2, 1 go question for everybody, and it's going to be a yes or no question. Do we expect this function to have any stationary points? Do we expect there to be any points where the derivative is 0? Yes or no? Your guess. 3, 2, 1, go. Okay, some people are playing the game. Thank you for playing. The answer is indeed yes. Why do we expect it to have some critical points or where the derivative equals 0? Well, this is a cubic polynomial with a leading coefficient that's negative. So that means that the graph either looks like this, right, which is minus x cubed, or it has some wiggles in it. And the wiggles are where the derivative is 0. So if this graph has some wiggles, if it looks like this, then there's going to be some places where the derivative is 0. It's possible that it doesn't have any wiggles, and we'll find that out soon enough. But we suspect it's going to have some wiggles. So let's look for them. So let's look at g prime of x. Well, you look at this, it's 0 plus 12 minus 3x squared. That's the derivative of g. Let's simplify a little bit. I'm going to pull out a 3. And so I've got 3 times the quantity 4 minus x squared. Oh, that's cool. And that's 3 times the quantity 2 minus x times 2 plus x. I'm just factoring it all the way because I can. So looking at this, we see the stationary points are plus or minus 2. Good. So there we go. Those are the critical points. That's our answer to question 1. Critical points are plus or minus 2. Question 2, what are the intervals on which g of x is increasing and on which g of x is decreasing? So for this question, we're going to make a chart of signs. So for the chart of signs, we're going to put a copy of the real line down. And on that real line, we're going to put all the critical points, which for us are minus 2 and 2. And then to the left of the real number line, we're going to put all the factors of g prime. So I'm just going to be pedantic, and I'm going to put all our factors here. I'm going to put 3, I'm going to put 2 minus x, I'm going to put 2 plus x. You'll see that it's kind of silly that we put 3 there. And as you get used to this, you won't put it there. Okay, so now I'm going to make my chart. And the idea here is at the bottom, we're going to have g prime of x. Because g prime of x is 3 times 2 minus x times 2 plus x. So since g prime is the product of all these things, we'll be able to use the signs of each of the factors to determine the signs of g prime. So let's do it. I'll do one of the factors, then I'm going to ask you to do the other 2 factors. So I'm going to do the simple one, 3. 3 is always positive, so all of those things are positive. That's kind of why it's silly to put 3 in here. If it were negative 3, then it might make more sense to put the negative signs in there. I'll let you decide through your practice. All right. Next row, 2 minus x. What are the signs here? Take 10 seconds. Well, I'll give you 15 seconds, and then I'll ask you to share in the chat if you have a sequence of signs, what you think they should be here. Anybody want to share with the class what you get? Throw it in the chat or vocalize it. Either way is fine. All right, 3 people have volunteered. Andre, Ali, and Jesse. Oh, here's some more. Summer and Robert. If math were a democracy, we think we would see what the pattern is, but math isn't a democracy, right? Math is different. But to some extent, you can use empirical data to do some mathematics. So it looks like the consensus is the sign should be plus, plus, minus. Let's check this out. So for the first box here, I'm going to plug in -3. So 2 minus -3, that's 2 plus 3, that's 5. So I say that's a plus. On the next interval, I'm going to plug in 0. And so 2 minus 0 is 2. I'm going to agree that that's a plus. And on the next interval, I'm going to plug in 3. 2 minus 3 is minus 1, so it's a negative sign. So plus plus minus is what I get. You good with that, Ali?
I didn't turn I did 2 minus 3, but I didn't make the minus like it was -1 instead of -5.
Yeah. Cool. So the next row, if we play the same game, I think we're going to get a minus, a plus, and a plus. Yeah. So I believe that's what we get. And then for the last row, we're going to do this. A plus times a plus, a positive times a positive times a negative is a negative. A positive times a positive times a positive is a positive. And a positive times a negative times a positive is a negative. So those are the signs for my derivative. And now I'm going to draw my little arrows in, being especially careful for the direction. So in the leftmost interval, my derivative is negative, so my function's going down, it's decreasing. And it's also decreasing on the third interval. And on the middle interval, my derivative is positive, so my function's increasing, so I've got my arrow going up. All right, so let's answer the question. So this chart of signs tells me the function g of x is increasing on the interval from -2 to 2. And the function g of x is decreasing on the interval from minus infinity to -2 union the interval from 2 to positive infinity. So here we're going to use that mathematical notation of union. And there we go. That's the answer to question number 2. On what intervals is my function increasing and decreasing? Oop, that's not what I wanted. Let's copy this over because we're going to use this for a third question. And the third question is, let's use the first derivative test to identify the function's local extrema. Okay, so first derivative test. The first derivative test it's going to tell us about the nature of the critical points. So we're just looking at -2 and 2 here. So the first derivative test tells us that x equals -2 is a local minima. And that x equals 2 is a local maxima. Okay, and that's what the first derivative test tells us. And we get that from our chart of signs. The fact that the derivative is changing signs at -2 from minus to plus, that means that it's going down and then going up. So 2 is a local minima. And at the other critical point, we're changing from positive to negative. That means we're going up and then going down. So 2 is a local maxima. And I think the last question was about sketching. Yeah, so let's sketch. So before we sketch, let's do this. Let's find the y-intercept. Let's plug in g equals 0. And I think my function was 5 minus 12x minus x cubed. That's plus 12x. So 12 times 5 is 60. So I've got 65 minus 5 cubed. Well, 5 cubed is 5 squared, which is 25. 25 times 5 is 125. So 65 minus 125 is minus 60. So I've got this really big negative y-intercept. So how about the zeros? How about the x-intercept? So I'll say this is the y-intercept. How about the x-intercept? So here we've got g of x equals 5 plus 12x minus x cubed. Oh, and we want to solve 0 equals this. I'm too low. Oh, wouldn't it be nice if there were a cubic formula for finding the solutions to a cubic equation? And there is a formula for finding equations of a cubic formula like this. But I'm going to tell you, if you see something like this, don't do it. We don't have methods that allow us to do this effectively. There is a method called Newton's method that we could use, but we haven't talked about it. So this is an example of where we'd be finding an approximation for the 0 anyway. So just don't worry about this right for now. We've got our y-intercept. That's good. The x-intercepts, we'll just fudge them. What else do we need? Well, we want the critical values of our function. So, so what's f of 2 and what's f of negative 2? So plugging 2 into our function down here, let's see if I can do it. 5 plus 24 is 29 minus 8. So 29 minus 8 is a 21. And let's do the same thing for minus 2. 5 minus 24, that's minus 19. Minus a negative 8, so it's a plus 8. So minus 19 plus 8 is a minus 11. All right, so let's do this. Oops. Come on. So we know at 2, we're up here, but about 21. We'll try to be proportional. So let's say this is a 21. And at negative 2, we're at negative 11. So I'm going to put this negative 60 way down here. So here's our negative 11. And we know that our function comes down to our first local minima, then goes up to our local maxima, and then it goes down. And we know that our function's a cubic polynomial. So we know it goes to infinity as well, it gets bigger and bigger without bound as the input gets bigger and bigger. So it doesn't have a horizontal asymptote. So this allows me to say, well, that the rough crude sketch looks like this. Oh, wait a second. What's wrong with this picture? You mean tell me what's wrong with this picture? So stupid. I am so stupid today. Yeah, Robert, you saw it, right? It doesn't intersect. What do you mean it doesn't intersect at minus 60?
Like the y-intercept is supposed to like be part of the line, but the line isn't even going through there.
Yeah, right. So if you look at this picture, there's no way in hell this has a y-intercept of negative 60. No freaking way can this thing have a y-intercept of negative 60 because the y-intercept would have to be smaller than the local min. Right? It would have to go down. That just doesn't make sense. So look at my work here. How is Miller an idiot this morning? What's wrong with this work?
You should have set x to 0.
What did I do instead, Robert?
You plugged in 5.
Yeah.
I was gonna ask you too. I was kind of confused about it. I was like, why is there a 5 in there?
Yeah, those should be zeros. Yeah, those should be zeros. So the next line should be 5. So we should get a 5. So that looks pretty good, right? The way I did my stupid rough sketch that seems to be what's a good word for it? Seems to be reasonable. Seems to be a good approximation. Okay, so now that that's fixed, I can say, well, let's go from my rough approximation to a better sketch. And my rough approximation has these singular points here, so I need to smooth those out. So I'm going to put green in here, smooth that out. And then I'm going to try to connect those two local extrema through my y-intercept nice and smoothly. And then I'm going to draw these branches of my graph. And I want to draw them in a way that doesn't suggest there's a vertical asymptote either. So I don't want them to get too steep too quickly, but there's a decent sketch. Okay. Now you could go to Wolfram Alpha and plug it into Wolfram Alpha and see what the graph of it looks like. So in a way, we never really use the first derivative test to sketch a graph. We really use this first derivative to do analysis to find out where local minima and local maxima are exactly. Wolfram, no graphing program is going to show you exactly where an extrema is. So the sketching part is something we do for free, and then it allows us to check our work by plotting with Wolfram Alpha. All right, we're almost out of time, and so we're not going to be able to do a breakout thing, but what I would have had you do, and this is what I'll just say you should try on your own. Repeat that last exercise for the function f of t, and I'm going to say is t squared plus 4t plus 5. Find its local extrema. Find where the function's increasing and decreasing. And you know a lot about what a graph of this should look like. And do the analysis, do the calculus, and it'll support kind of what your gut feeling is for what the graph should look like. And do this on its domain, like we did on the last example, and then do it on the interval from -5 to 3. Okay. So to understand, how do things change if you go from its domain to this interval? That'll be good practice. And you can email me with your thoughts on that if you have them. And we're gonna end a couple minutes early because there's not much that I could do going into another example. But the next thing we're going to talk about is something called the second derivative test. For extrema. And the idea is this. We've talked a little bit about the second derivative. And in the context of velocity. If you have a position function and you take its derivative, you get a velocity function. And if you take its derivative, which is the second derivative of position, you get an acceleration function. So what an acceleration function is telling you is the rate of change of the velocity. So in abstract terms, if you've got a function, the derivative is the slope of the tangent line. And the second derivative is the rate of change of the slope of the tangent line. So if you drew a function like this, your tangent lines here are increasing. So the derivative of the slope of the tangent lines is positive. So this is an example of where the second derivative of the function is positive. Okay. Tangent lines increase in slope. And we call this behavior concavity or concave up. And similarly, when the second derivative is negative, we say a function's graph is concave down. And this means that the slope of the tangent lines is decreasing. So you might have this happening. So we've got a tangent line here, and the next tangent line has got a slope that's less and a slope that's less. So concavity talks about curviness. Oops. The first derivative test just tells you about straight lines, and concavity tells you about curviness. This leads you to the idea or the question of what does f prime or f double prime equals 0 tell you? Well, it's where a function changes from being concave up to being concave down. Right? Concave up means the second derivative is positive. Concave down means the second derivative is negative. So it changes sign where the second derivative equals 0. And this is called an inflection point. It's the analog to critical point, but for the second derivative. Inflection point is a term that you hear kicked around a bunch in the popular press sometimes. For example, right now, COVID cases are increasing at an increasing rate. What we want to see in those COVID curves is an inflection point where they might start increasing, but then they're going to start decreasing because that is a precursor to them going down. So concave up infection rates, bad. You want to see them switch to concave down, so then they'll eventually start to decrease. Anyway, that's one example of where the term inflection point gets kicked around in the popular press. And it's a Calc 2 word. What these ideas are going to allow us to do is test for local maxima. So here's a local maxima. The curve is concave down. So if you've got a critical point and your second derivative is negative at that critical point, then you're at a local max. This is what the second derivative test tells us. If you've got a minimum and the second derivative is positive, or if you got a critical point and the second derivative is positive, then that's a local minima. Right? This is the second derivative test. We'll talk about that next time. We'll do some examples like we did today, but we'll add in a second derivative variation of it. And that will allow us to start putting curviness into our graph. It'll tell us exactly, precisely where our graph curves. Today, I was just eyeballing it, right? I was just making it up. The second derivative will give us more information about concavity. And so just like today, we had a chart of signs for the first derivative, we're going to add in a chart of signs for the second derivative so we can keep track of where things are concave. All right, that's where I will stop today. Thank you, everybody. I hope you continue to stay well. We're almost done with the semester. Some people have come to me with concerns about grading and things. I want to let you know that there are certain cutoffs in the syllabus for, here, I'm going to stop sharing my tablet so you can see me. There are certain cutoffs for grades in our syllabus. Right now, the cutoffs are right here. I'm going to start moving them down. So be prepared for an adjustment. Okay. So what this means is that you'll be able to, the amount of learning target quizzes you've taken and passed to show me you've mastered learning targets for the course, it's going to earn you a higher grade right after I make this adjustment. So be prepared for that. If you have concerns about where you are in the class, please talk to me. Some people have reached out to me about that right now. I think my adjustment for the cutoffs will help you feel better. And so it will help me to know who's concerned and who's not. And just I'm here. Send me an email, come to office hours or student hours or whatever. And let's talk. Jet asks, how many quizzes are there going to be left? Well, we'll probably have the 3 more that you wanted me to post. I'll put up a bunch of other alternate versions for learning targets. And then I'll probably add 4 or 5 more from the last subject in the class called integration. No, actually, there'll probably be like 6 or 7 more that are up there. So there's going to be a good number left. I need to think about that before I adjust these cutoffs.
I had a quick question. Sorry, it's like kind of
Yeah.
unrelated. I just realized I needed to do my registration, and next semester is spring 2021, right? Not winter. I'm sorry, this
Correct.
is so random. Okay, because winter popped up as an option. I was like, huh.
Yeah, we're on the semester system. So winter is a weird little small window of things. Like I think education might have some classes in winter, but yeah, you definitely want spring.
Okay, I'm sorry. That was super random, but thank you.
No, I'm here, right? I mean, I'm one of the university people that you get in contact with. So yeah, just ask me anything that you need to ask me. And
Thank you.
we're done anyway. You bet, Summer. Okay, let's call it a day. I'll be available online. Lupe, drop in, work with him, and keep taking those learn at target quizzes. Show me you're mastering this stuff. Practice, and show me you know it.
One more thing. I'll be in your class next semester too. I already have like the class in my cart for
Hey,
Monday
great,
or
Robert.
Wednesday. Yeah.
Sweet. Good to know. More people should follow suit.
Yes.
All right. See you all on Wednesday.
All right.
Bye-bye. Stuff good with you, Lupe?
Yeah, this is more of a student question.
Sure.